We next look at a determinate structure, a cantilevered beam, as you see on the screen, supported at point B and subjected to a uniform dead load D and a point load, a point live load L at the free end C. So our understanding of the mechanics of the beam tells us that it can fail in three modes: flexure, shear, and excessive deflection. We are ignoring other failure modes, for example, lateral, torsional, buckling. So which failure modes to be considered in a reliability analysis has to come from our understanding of the mechanics and our experience with similar situations. So our understanding of the mechanics of the problem also tells us that in order to evaluate or consider flexural failure, we don't need to look at the entire length of the beam at all possible cross sections, but the most critical cross section is the support B. Likewise, for shear failure, it is the same support at B, which is most likely to fail in shear if it does. Likewise, the point at which maximum deflection has to be considered is the tip at C. Thus, although this is a distributed structure, we have reduced the scope of the problem considerably by using our understanding, our experience, and focusing on just two critical locations, point B for flexural failure, point B again for shear failure, and point C for deflection failure. So we are not going to look at all the other cross sections throughout the length of the beam. Now let's take a look at these three limit states one by one. For bending, the applied moment at B is L times the length plus the contribution of the dead load, dl squared by 2, and the bending moment capacity of the beam is its section modulus S sub z times the yield strength. Now the S sub z, depending on our understanding, our preference, and also the mechanical properties, could be the elastic section modulus or the plastic section modulus. Now, whichever that is, bending failure would occur when the applied moment exceeds the moment capacity. So that would be setting up the failure description for the beam in flexion. Let's look at shear next. The applied shear force is L plus D small l at B, and the shear force capacity, we choose to define it as 0.6 times the air resisting shear times the yield strength of the material. And shear failure occurs when the applied force exceeds the shear force capacity. Finally, for the deflection limit state, we choose to do an elastic analysis. So you see the well-known result. The tip deflection delta is given is the sum of the contribution of the dead load and the live load, where we have used the bending rigidity EI for the beam. Now, the maximum allowable deformation at point C, let us say it's L over 100. Again, it depends on the application of the structure, what sort of purpose it is going to serve. So let us say it's the length over 100, and deflection failure occurs when the tip deflection delta exceeds that limit L over 100. And so this way we have defined the failure of the beam in terms of a series representation. the system failure is the bending failure or the shear failure or the deflection failure. So now we are ready to take up the next stage of the analysis, which we will look at in a week or two in analyzing the reliability, in computing the reliability of this structure. Let's see what would happen if we bring in an explicit time aspect to the problem. We have the same beam, the cantilevered beam supported at B, subjected to dead load, the distributed dead load D and the point live load L, but L is no longer time invariant quantity. It changes with time, and let us say that it occurs as pulses, as short pulses during the life of the structure for very small durations. It could be the occurrence of vehicles on part of the bridge structure or other loads caused by human activities. The dead load D is still time invariant. So if we were to draw a sample function of what's happening, this is what it would look like. The dead load D, it doesn't change with time. It's a random quantity, but it doesn't change with time. It's sampled from the distribution D that you see on the left. The live load L, as I said, occurs as random pulse load. So it's added to the dead load, but it's not invariant in time. It's sampled from the distribution that you see on the left, but the peaks are all random. The locations, the instances of time where these pulses occur are also random in nature. Now, something else could also vary in time, and that is the capacities. Let's say we're talking just about moment capacity. So the moment capacity C is also not invariant in time, but it decreases maybe randomly in time, say due to processes like corrosion or fatigue crack growth. So here we have drawn a few sample functions of that deteriorating capacity C. Now if you, in a very naive manner, if we just add D and L, so the points in time that the red tip crosses those black capacity lines would constitute to be a failure. So now we just cannot have a very compact description of failure, but failure would look something like this. We need to take into account the moment capacity as it changes with time. So it's the S sub Z, the section modulus, which is now a time-dependent function, maybe time-dependent random function, and the applied moment, which is now it depends on the time-dependent live load L. So now that checking of whether M applied is more than M capacity or not, it cannot be done just once, but it has to be done theoretically at all instances of time. So obviously it's an infinite dimensional problem, but we can shorten that. We can reduce the dimensionality if we just look at the instances of time that L occurs. And then if we look at all such instances of time, then we would have a proper description of flexural failure of this beam. We should do that something similar for the shear limit state as well as for the deflection limit state. So this, if we have such a time-dependent problem, this would be a way to set it up. And then simplifications and computations would come next.